Okay, so yeah, we're going to start with the introduction to information theory now. To talk about information, first we need to understand probability. So we'll just start with just 2-3 definitions, okay? So we're going to just talk about the difference between a random variable and a distribution over a random variable. So as far as the notation goes, we denote a random variable with just a capital X. And so our random variable is supposed to contain all the possible, events or outcomes. So event 1, event 2, and so on. And now either our variable is a finite random variable, so we would have a finite number of events, or it's a continuous random variable. So say it's like it's like it can have infinite different outcomes. So for example, say a finite random variable would be something like a roll over ice.
Yeah.
You cannot have something that is between 5 and 6. However, if I had a random variable that is talking about the height of children, it's not always the case that I will have 5 feet, 6 feet, and nothing in between.
Yeah.
So when you have an infinite range like this, or you have something like an interval, this is called a continuous random variable. For the purposes of the video, do you want to name 2-3 other examples?
Continuous.
Continuous and finite.
Yes. Fuel economy, continuous.
What is?
Like average fuel economy or something.
Economy.
Yeah, like I don't know if I'm making much sense right now.
What are you saying?
Over a given set of vehicles, the average fuel efficiency is not.
Do you think you could text it? Because I can't tell what you're saying.
Oh, is the mic that bad?
Yeah, no. Like when you say words, I can hear it, but then when you say the example, I can't.
Oh, okay.
Yeah.
Let me just.
What's your example again?
I misheard you.
I didn't hear that. I need you to type it.
Hey, I texted you.
Oh, not on WhatsApp, in the chat.
Oh.
I can't use my phone right now.
Okay.
Yeah. Have you sent it or?
Yeah, I just did. Your message wasn't relevant. Wow.
No, I mean like in the Gmeet chat.
Yeah, you said it said your message is not relevant.
Okay, fine. I'll just go ahead and give some examples then. Fine?
No.
Okay, fine. Let's just consider weight. This is one continuous variable. Can have you can have someone's net worth. That is also in some sense a continuous variable. because you have infinite cases. There's no upper limit to how much money someone can have. So virtually you can have infinite money.
Yeah.
Unless you decide that, okay, 1 trillion is finite enough for all practical purposes. And so I will consider 0 to 1 trillion cases. So in that case, sure, you can call it finite.
But even within that, you can have an infinitesimally small difference in the amount of money.
I really can't hear you. It sounds very muffled. Blink twice if you need help.
Better now?
Okay, say what you're saying again.
Is it better now? Okay.
Oh, much. Miles better now.
Okay. I was just on mic. So, yeah. Like, technically, even within a trillion, you can have an infinite amount of...
Yeah, within the trillion, you have decimal. And you can technically take these decimals as far as you like. So, yeah. For all practical purposes, this is a continuous random variable. Let's take some finite random variables. Our friendly deck of cards.
Yeah.
Dice rolls. What else? Basic examples. Coins. Or a collection of coins.
Yeah.
Okay, cool. So these are some very basic examples. Now these are all random variables themselves. So if I say, so what I want to distinguish between is statements about a random variable versus statements about its distribution. Now, the first thing you literally think of whenever you think of coins is the distribution. Okay, it has 1/2 chance of being heads or tails. Right?
Yeah.
However, this is a statement that we do not make about the random variable itself. This is a statement we say about the distribution. That the probability of us getting one outcome versus over another is 1/2 for each of them respectively. Right? A statement about the random variable is, say I just I had a coin like this. Okay, I flipped it. Initially I knew the sides, say this is something like heads. Now I don't know what this is. So for me to make a statement about this is like saying this is this outcome is heads. So that's a statement about this variable alone. And this is a statement that is strictly either true or false. Make sense?
Yeah.
So there's a distinction between making statements about your variable over making statements about your distribution. Your statements about your distribution do not change regardless of the outcome of your variable. So if I made a statement like this is heads, it can be true or false after I look at the actual outcome. So now I'm going to see that this is actually heads, and then I'll be like, okay, this is true. However, if I say that the probability of each outcome, or let's just say the probability of heads, just to be consistent, is 0.5. Now, regardless of the outcome of this statement is true. Because it's a statement about a distribution, not about the random variable itself. Okay, so we have that distinction clear?
Yeah.
Okay, great. I will just delete this, hopefully without trouble. I'll pause the recording, I just need to get my charger. Okay, I'll just delete everything. Awesome, right. Okay, so now that we know why a random variable is a statement about a random variable. Is different or different from the statements about the distribution over which my random variable is sampled. So only when you make an actual change to your distribution, only then you can change statements and determine if it's true or false, like stating that the probability of heads is 1/2 is always true unless I make one side heavier than the other.
Yeah.
Right. So as long as I have a fair coin, unfair coin.
Probability.
And this act of introducing an unfair coin is the act of changing a distribution. In simple terms, you're making the other outcome more likely than this outcome. Less likely. Oh no, it's the other way around. Let's say because I'm weighting this side, I'm making this have more mass. So, okay, just to forget about the technicalities, it just changes. Yeah, technically, yeah, because I'm adding more mass to this, I'm making this less likely. But for now, we will just ignore that because my main point is about that we're changing distributions, and then and only then we can change. We can, change whether this statement is true or false.
Yeah.
Okay. Now, I would like to introduce the information aspect. So typically, in the problem of information theory is called the problem of information transmission. And that is, say, according to that paper, say you have a party Alice and you have a party Bob. Say Alice has some message. What Alice is going to do is she's going to put it in some sort of encoder. That's going to give us a coded word or a code word. This code word is, in the problem of information transmission, going to go through a channel, like how we saw in our physics cycle. It's going to go to a channel that introduces noise to our code word. So you should expect an erroneous code word. Or more technically, since we're just receiving this word, we call it the received word. It's now Bob's challenge to decode this word and give the original message. Now, one thing I want you to note is that not exactly an intuition. However, okay, this thing could just scroll to make my life easy. Right, there you go. Okay, so one thing to note is that our channel is basically the problem, right? Now, intuitively, does it make sense that if I have a word 1 and if I also have a word 2, let's say the length of word 1 is less than the length of word 2. Which one is more erroneous? Which has
the second
more errors? Yes, exactly. The second one is going to be far more erroneous than the first one. And hence, we have a goal that was listed in the paper that was about minimizing the length of our word. Or more specifically, we would say bits, the number of bits. Okay? So, now, the fact that there is noise being added to this means that this channel is introducing some sort of non-determinism. And now we will just go to just a vague definition about what it means to be deterministic and what it means to be non-deterministic. Okay. So, determinism versus non-determinism. Excuse me. Right, okay. So what does it mean to be deterministic? It means given the same set of initial conditions, say my initial conditions is something like these x naught, y naught, z naught, some point. Okay? So I should get the same if I put it under some sort of deterministic function. And I should get f of x naught, f of y naught, and f of z naught. And no matter how many times I do, keep doing f, I should get the exact same output. Moreover, if I have some sort of deformation, if I go around a small neighborhood of these points, G, okay, and I do the same f business, the distance between, let's say this point is P, this point is some P star, then the distance between P and P star should not be large. And now I will show you two non-deterministic models that violate this. That is if this scrolls. I don't know why this thing has to lose its mind every time.
Isn't it supposed to have infinite scrolls? Isn't it supposed to have infinite scrolls?
Infinite?
Scrolling.
It is. It's just that every time I switch from the tab to the cursor, it goes wild and it tries to select every character I've written. And what ends up happening is if I scroll just normally with my fingers, it drags everything until it looks like some sort of curse. Anyways, so there are two largely studied models that are non-deterministic. So the first one is probabilistic models. And that's easy. You just take something like a deck of cards, right? And if I sample one x1, x0, xn, then there is no condition that any of them are equal.
Yeah.
And more often, if you're sampling from the same deck, then it's more likely that it grows less likely for any of them to be equal.
Yeah.
Because if I saw an ace, I'm not going to see an ace again, at least for a long, long time, until I run out of cards.
Right.
Next one is a chaotic model. And so in a chaotic model, this principle of initial conditions is violated. If I have something, oh yeah, I forgot to just bound this. So this D has to be greater than 0 and it has to be less than some epsilon, where epsilon is a very small number. That's what it means for it to not be large.
Yeah.
Anyways, so in a chaotic model, D P of P comma P star is going to be very, very large. And so that's why you see, like, in a double pendular system, if I start from, say, this sort of position versus if I start from, say, this sort of position, I could end up in very widely different cases, right? So that's the whole point of chaotic models. So deterministic models are this sort of like, really nice, very well behaved stuff.
Yeah.
Right. Okay, now with that said, I shall attempt to scroll once more. I'm going to kill myself someday and I'm going to put this on my grave because OneNote couldn't fix their scrolling issues. Okay.
Yeah.
Okay, so now that's why when I have a message over here from Alice and I have an encoder. Let's say an encoder is basically a function and it gives me some sort of f of message. Right. So the issue is, if f is deterministic, then whoever is trying to intercept the message from some outer party just has to know what this encoder is doing. And so he can just basically look over at what you're doing and he can just decode it himself separately, decodes independently. And then your question becomes about how you're going to hide this. And then eventually you're going to use some sort of, again, deterministic method to hide this. Then again, you're going to introduce some sort of G, which is some sort of thing that hides this. And you're going to try that with another deterministic thing, H, and that list keeps on going on without resolving the actual core issue.
Yeah.
So by staying deterministic, there's no way to actually go around this problem. Now, the second option is, without going directly to probabilistic, let's consider what happens when we say f is chaotic. Then it is vulnerable. However, if f is chaotic, although it seems like at least no outer party can figure out, the problem is Bob can't figure out what you're doing either.
Yeah, because there's no way you can determine.
Yeah, so you can't recover something, especially if there's errors being added midway. So you cannot recover whatever you had. So not only Bob can't figure out what you're doing, not only the outer party can't figure out what you're doing, it's secure to Bob as well, to whom you're trying to send the message. Oh wow, I didn't. Alright, there we go. This is not connected. Okay, there we go. Right, okay. And this is why we consider that f is probabilistic. Because in some sense I'm going to Alice and Bob are going to have certain statements about their distribution that they both agree on. And so whatever they send between each other, if that whatever they send still satisfies statements from these distributions, you can say that, okay, the message has more or less gone through without errors, or there is some way to actually recover what you're doing if you both have basically the same starting distribution. That's why on the first page of the book, of the paper, he has something that looks like this: x0, p0, x1, p1,
Yeah.
x2, p2. Then he continues it for a finite number of characters. This is essentially a statement about agreement, or an agreement in distribution. So Alice and Bob both know these. Alice as well as Bob agree on this fact. And this is the starting point of how you want to think about how information transfers happen. Okay? So far, so clear? Any sort of like weird contradictions that come to mind?
Okay, see now, you know the probability of each thing occurring, but how exactly are you, like you send it as a distribution, send it as a probability, like what's going on? Exactly?
Oh, so basically as Alice is over here, Bob is over here, you have some channel in the middle.
Yeah.
You have your message over here, he has his output over here. You send it to a decoder or an encoder first. Encoder.
Yeah.
He receives it from a decoder. This is your received word. And this is your code word. So what happens is your code word is some sort of encoding that gets sent bit by bit.
Yeah.
And so along with just this distribution alone, like I said, it's only a starting point. But what they also do is they end up coming up with some sort of common way. Okay, I'm going to encode this in certain sort of way that is not deterministic, or I'm going to encode in this probabilistic way. And that information of how it's encoded probabilistically is known to Bob. And so using that information about how it's probabilistically encoded, he's going to decode what he receives. Okay? Okay, cool. So like I said, the transmission from a code word to a received word happens bit by bit, right? So I'm going to start last one first. So I'm going to send 1, I'm going to send 0, 1, 0, 1, 1, 1. And Bob is going to receive the same thing, maybe with some errors over here and there. So I've included one error over here in this character.
Yeah.
Right? Now, what we're interested in right now is about this string. How do we define it? So, we want to come up with a notion of words. How do we define words? We define words with letters, right? And so, in this case, the letters of this encoding are just plain 0 and 1. Right? The set of letters. And so if the letters are 0 and 1, we call the set of letters an alphabet. Okay? Do you want to note this down?
Yeah, I have.
Okay, I'll just delete it then.
Yeah. Yeah.
This thing really has a mind of its own, man.
Yeah, like.
Did you see? What a...
Yeah, it
just glitches its mind off. Okay, so let's continue with the notion of a word. So we start with alphabets. An alphabet. So an alphabet is just a set of letters. The ones that are of interest to us today are the ones formed by just 2 letters like this. This is the one you will see in the paper.
Yeah.
Another one of interest to us that will give us actually more interesting examples is this one, and so on, right? I can have as many different letters as I want, and I can combine them. And now we need to define how do we combine. Exactly. So we concatenate letters to form a sequence. So if typically, at least in the books I studied, we denote alphabet as sigma.
Yeah.
However, in the paper, you'll see it's referred to as X. Okay, which I find confusing because I almost always use it for random variables. So no. Then an alphabet, like we said, is a finite set.
W.
What is W?
Like if you have a problem with it, wait, your voice broke in the middle. You just mean a sigma is what you're using.
So, what did you want to ask? I haven't said anything too important. I've just said that the notation is sigma. That's it.
Okay. Yeah. Okay. Wi-Fi missed a bit there.
Right. Okay. Now, from a set sigma, I can construct something called sigma star, which is the set of all finite sequences formed by sigma. So this is basically the set of all words that is formed by sigma. So let's consider the example of A, B. Then the first word, that is, I can have absolutely no characters at all, and that is called the empty word. Similarly, I can construct A, B, A, B, B, A, B, B, A, and so on. Now, although these are all individually finite, one thing to note is that all sequences are finite, but that may not imply that sigma star is always finite. It's not always finite. So in this case, when I'm not restricting any of my words, I'm allowing basically any combination on the face of the earth. This is infinite.
Yeah.
Right? Whoa, gosh. Wow. What even?
Hey, it worked.
What is going on here? Okay. Right. So, sigma star is simply all the collections. And now, given a sigma star, I'm going to define something called a language. So, a language is a subset of sigma star. And basically, as long as I have some sort of valid just way of defining this subset, then I have a valid language. So, for example, I could say my language LAA is going to consist of is a set of all words such that and there is a substring AA in my word. So that would include words like this. Later on, if I had something like AAB or BAA, these would both all come into this subset. And as long as I'm not putting any additional structure, this is perfectly valid as a language. Okay?
Yeah.
Now, let's talk about, for the rest of this session, we'll just consider examples of languages. And so what you and me are going to do, we're going to just construct interesting subsets of L is a subset of sigma star. Interesting subsets slash L. Okay. And now for the great scrolling.
Yes.
Okay, there you go. That was less
Nice.
painful.
For once.
Okay. So one language examples. So I have an interesting example to talk about. Let's consider an Ln, subset of our sigma star, where, okay, let's also consider our sigma is equal to, say, number 0, 1, 2. Okay? So, where the sum of the letters belonging to the word, where the word belongs to sigma star, or no wait, where the word belongs to ln specifically, sums to n. What does that mean? If I have, say, something like L2, or let's say L3, that's a little more interesting. So L3 is going to not consist of the empty word. It's going to consist of 1, 2, 2, 1, 0, 1, 1,
0,
1.
1, 2.
Yeah, 0, 1, 2. Oh yeah, I can basically add 0 to any of the existing ones and I can have a new word. So 2, 1, 0, I can add 0 on either sides. And so this is somewhat an interesting combination. Similarly, I can construct L4, Ln as whatever I like. And I can even change what I want for my alphabet. So this is just base 3. Similarly, I can consider a sigma n, where it is the set of base n integers. Okay? Make sense?
Yeah.
Now, because I don't want you to come up with a new example like just yet, so let's try to play around in this rule, okay, that we've imposed on it. So you and me, let's just consider that this is exactly the same, that we're going to have some sort of ln and some sort of sigma n. I want you to try to come up with alternate rules like this. Okay?
Okay. You can have a product that sums to something.
What do you want to? Product. Okay, awesome.
Like words where the product of the individual letters. Yeah.
Okay, wait. Let me just... Wow, God help me with this thing.
Are you using a drawing pad or something?
No, I'm just struggling to get the eraser. Because I can't delete the whole thing.
Yeah.
Oh, Lord. Jesus. What is even going on, man? Okay, finally.
Yeah. Alright, damn.
Oh, Lord. Okay. Okay.
You can have it where the product of the individual letters multiplies up to 2 power of that. Or I don't know if that's too specific.
That's not specific at all. Not too specific at all. It's a perfectly valid definition. Product of
2 powers the length of each of them.
Is, what is it again? 2 to the power of each of them.
Yeah.
So...
not of the individual word length.
So do I...
of the base end.
Okay, wait. So, help me understand. Am I going to do 2 of D1 plus...
2 power n.
2 power n. Oh, okay. That is interesting. Yes, okay. So that is interesting. Yes. Okay. So in this case, L3 would be something where, let's scratch these all off because I'm not going to erase again. I'm traumatized. Right. So we would consider words like 1111. Okay. Where it's done 8 times. We would consider 22224 like that. We can add zeros anywhere in between and around this to get the whole set.
No, that does matter here because the product ends up being 0 then. No?
Oh, true. Oh wait, yeah, product, right. I'm still thinking in terms of sum.
Yeah.
So that would be 222.
Yeah.
Then I can add 1 on any places over here. But you know what's an interesting thing? Actually. No word that belongs to ln actually. ln is going to, okay, 0 does not belong to any of the words that belong to ln.
Yeah.
So by that you've basically rejected every single word that contains the letter 0. Very good.
Yeah.
Okay. Any other examples? So similarly, I can have a whole class of examples where I take, instead of 2, I can take 3, 4 or any other integer k.
Yeah. You could have any function that you play with this one. Like you have you take each of the words as, each of the letters as an element, you add them, then subtract them, multiply them, you can, have your way with it.
Yeah, basically, wait, what do you mean exactly?
Yeah. As in, we can define any function.
Yes, true. We have basically free will with whatever we want.
Yeah.
Okay. So, it's almost time for the next lecture. So what I'll do is I'll leave with one small statement. And one of the weakest structures under a language is something called a regular language. And a regular language is a language that L is a regular language if it can be recognized by a deterministic finite automaton. And this will be the topic of our next lecture. That, along with more contents from Jaishankar's notes. More from Jaishankar. Okay, cool. So I'll stop here.